Dear students, we are going to talk about double integration today. So, double integration is extension of single integral into two dimension. So, you are already familiar with the single integral that I have just noted here. So, a to b y dx is equal to a to b f of x dx. Y is equal to f of x is the function. It is taken over here. Then what this single integral, we usually write a to b definite integral dx f of x dx. So it is representing area bounded by the curve y is equal to f of x is equal to a line, x is equal to b line and under x axis. Similarly, if you would like to write down area under y axis, then you might have learned in 12th standard a to b x dy. It is something like this. A to b, it is f of x, f of y into dy. It's something like this. So this is area under something like this. It is under y-axis, and this area, basic application of single integral is to find out area. Similarly, double integration also, if you have got some complicated region of integration, this is not under x-axis or not under y-axis. The region is located somewhere here. So we used to find in 12th standard just subtracting those two regions and we get the required region. But it is rather complicated job. So we introduce the double integration. So double integration, we need to find, it has many applications to find area, center of gravity, moment of inertia, center of pressure, etc. So basically we used to find mass. Oh, rho density, which is mass per unit area, it is given dm upon dm, it is rho dA. You can find out this by single integral also. Mass m, total mass, it is elementary mass, double integration r, rho dx dy. Rho is this function actually. Rho is function f of xy. So you can find out mass of a lamina depending upon the density over there. Similarly, center of gravity, moment of inertia, centroid, center of pressure, area, you can find out by double integration. Now, I give the definition of double integration. Let f of xy be a continuous function defined over the region R, or it is sometimes called domain also, bounded in x or y plane. Then the integral of this particular form, double integral R, f of xy dx dy, is called double integral over the region R. Now this domain R or region R, we have, it has three cases to discuss this region depending upon x variable, y variable boundary, and both are having constant boundaries. So three cases over here to evaluate the double integration. So case number one, so three cases. Case number one, it is something like this. You are having R, this region, it is y is equal to, y having the variable boundaries, y is equal to f2x, x is equal to a, x is equal to b. So this is the one of the possibility there of the region R. I draw figure for this. It is something like this. So if I take these boundaries here, y is equal to, this is y is equal to f1x, this is first curve, this is y is equal to f2x, and here x is equal to a, x is equal to b. So this is region of integration. This region, it is bounded by this line x is equal to a, this line x is equal to b here, this is x-axis, this is y-axis, and this is origin. So we have to find out this region of integration, means we have to evaluate the double integral over this, maybe some physical quantity there. So for this, what to do with this? So region R, I is equal to, this is basic definition of double integration, R, some function f of xy which is having, it is continuous over the region R bounded by this boundaries there. So I just insert these limits there. Y is equal to f1x to y is equal to f2x, x is equal to a, x is equal to b, then f of xy, dx dy, dx dy. Now it is kept in mind all the time. If y having variable boundaries here, if you observe, then we have to integrate the given integrand, the function, with respect to y first, keeping x as a constant. So I put this in variable separable form. That form is x is equal to a to x is equal to b, then y is equal to f1x to y is equal to f2x, and f of xy, this is with respect to y. Naturally x remains constant, then with respect to x. So if you integrate this, then you are getting this x is equal to a, x is equal to b, then this is function of x you are getting. If you integrate this with respect to y, keeping x as a constant, this is naturally a function of x, and you are getting this as a single integral. And you know, single integral, how to integrate this? This is equal to, it is some say integration of f of x is equal to phi of x, say primitive of this plus c. Then we write down this as phi of x and limits applied a to b. So value of this integral phi of b minus phi of a. So this is value of this integral. So this is the way we just discuss this. Where this occurs the region of integration with y having variable limits, x having constant limits. Similarly, case number 2 we are having here. Case number 2, y having variable limits and x having constant limits. In that case, all the time we integrate with respect to y first. Case number 2, region R is bounded by x is equal to f1y, x is equal to f2y, y is equal to c, y is equal to d. Naturally, this region would be as shown in the figure. It is something like this: x-axis, this is y-axis, this is origin, then x is equal to f1y is this curve, x is equal to f2y is this curve, this is y is equal to c, this is y is equal to d, y is equal to c, y is equal to d, and this is x is equal to f1y, x is equal to f2y is another curve here. Then this is the line, this is the street taken over here, and so this is region of integration. So this shaded is the domain or region of integration. Okay, maybe it is called as A, B, C, D is the region of integration. Now to integrate this, what we do here, the procedure to evaluate this type of the integral, it is something double integration R f of xy dx dy, that is the basic form of double integration. Now this is, now if you observe this, I insert the limits, x is equal to f1y, x is equal to f2y, x is equal to f2y, y is equal to c, y is equal to d, f of xy, and this is to be integrated with respect to y first, keeping x as a constant. I'm sorry, with respect to x first means dx, dx, and then dy. So because x having variable limits here, x having variable boundaries, so we integrate with respect to x first and then with respect to y. Y is equal to c to y is equal to d, and this is naturally function of y you are getting. If you integrate this, this is with respect to y. So this, if you evaluate, you are getting this as a function of y, because while integrating with respect to x, y regarded as a constant. If you apply the limits, then you are getting some function of y there. So this would be, it is something, if I take integration of or derivative of f of y dy, this is equal to phi of y, then this would be phi of y, limits applied, it is c to d here, by fundamental theorem of integral calculus, upper limit minus lower limit phi of d minus phi of c. So this is value of this integral. So this is the way you can just find out value if this case occurs, x having variable boundaries, y having constant boundaries. So this is important step. So variable separable, first you have to integrate with respect to x first, because x having variable boundaries, and if y having variable boundaries, then you have to integrate with respect to y first. So that is the basic, that is the key idea here to integrate any double integration. But there is case, that is case number 3, where x and y having both constant limits, where the domain, case number 3, it is something like this, double integration r, x is equal to a, x is equal to b, y is equal to c, and y is equal to d. So here, so this region of integration would be something like this. This is x-axis, this is y-axis, this is origin. X is equal to a, x-axis means y is equal to 0, y-axis means x is equal to 0. This is equation of x-axis, this is equation of y-axis. Now, I just write down this as x is equal to a line. This is parallel to y-axis, and x is equal to a, x is equal to b. Sorry, this is x axis, y is equal to 0. So I take this as, this is x is equal to a, and this is same, x is equal to b. B is greater than a, suppose. Then we take y is equal to c, and this is parallel to y-axis, x-axis, and this is y is equal to d, and this is region of integration. This is region of integration, it is R. Now here you can take any of the, with respect to x, with respect to y, it does not make any difference there. So if you integrate with respect to x or y, so this is region of integration, a, b, c, and d is the region of integration. A, B, C, D is the region of integration. So you can write down this as double integral I is equal to double integral R f of xy dx dy. This is equal to x is equal to a, x is equal to b, y is equal to c, y is equal to d, f of xy dx dy. Now here you can integrate with respect to x first or y first, it does not makes difference, or this implies I just write down, it is something like this, x is equal to a to x is equal to b, f of xy into dx, and then this is y is equal to c, y is equal to d into dy. This always equals to, so it is something like this, y is equal to c to y is equal to d, f of xy into dy, and this is then with respect to x, or the limits x is equal to a, x is equal to b. So from this one we will observe that it does not matter whether you integrate with respect to y, with respect to y first, or with respect to x first, value would be same, because this is with respect to x first and this is with respect to y first. So value of the integral is same. So this is very important. If the x and y having constant boundaries, then you can integrate with respect to x first or with respect to y first. It does not makes any difference there in the value of the double integration. Similarly, if you are having case number 1 where y having variable boundaries, then you must integrate with respect to y first and then with respect to x. Similarly, second case we have discussed here. If you if x having variable boundaries, then we integrate with respect to x first, the whatever means with respect to x first and then with respect to y. So in general, we have to integrate the given double integration with respect to the variable whose boundaries are variable, whose limits are variable, and then with respect to the variable whose limits are constant. So this is the way we just follow the procedure to evaluate the double integration. Now let us see some illustrated example on double integration. So the first example, evaluate the following integrals. Evaluate the first one. Zero to one, 0 to 1, 0 to root of 1 plus x square dx dy divided by 1 plus x square plus y square. We have to find out value of this integral. So it is very clear. This is say I, and these are the limits for y here, because y as a function of x. So I can write down this as I is equal to the integral y is equal to 0 to root of 1 plus x square. These are the limits for y. So first with respect to y, divided by 1 plus x square plus y square. Because y having variable limits, y as a function of x, and then with respect to x, over the limits x is equal to 0 to x is equal to 1. Now x is constant, so I will consider this as a constant. So I consider let 1 plus x square is equal to some constant, so I consider this is m square. This is temporary constant, x is equal to 0 to 1. So I write down once again y is equal to 0 to m, because m is equal to root of 1 plus x square. So I put this m dy upon m square plus y square, and this is with respect to x. Okay, next. So I integrate this by using the formula. This is equal to 0 to 1. So integration of this, it is 1 upon m, 1 upon m tan inverse of y upon m. This formula, limits applied 0 to m into dx. I apply the limits 0 to 1, 0 to 1, 1 upon m, the tan inverse of 1, tan inverse of 1 minus tan inverse of 0 into dx. So this is equal to x is equal to 0 to 1, 1 upon m means root of 1 plus x square, and this value tan inverse 1 is pi by 4, tan inverse 0 is 0 into dx. So I take this pi by 4 outside here. Pi by 4 is constant, and integration of this is log of or ln of 1 plus x square, and limits applied 0 to 1. So you are getting this as pi by 4, pi by 4, pi by 4 log of 1 plus 1 minus log of 1 plus 0, log 1 is 0. So you are getting this as pi by 4, pi by 4 log 2, pi by 4 log 2. So this is value of this integral. I'll see some illustrated example to evaluate the double integrations. So the first example, 0 to 1 dx dy divided by root of 1 minus x square minus 1 minus y square into 1 minus y square. Now this integral I would like to evaluate. So limits are constant. So as I said earlier, we have seen 3 cases to evaluate the double integration. So this is case number 3, limits are constant. So we can put this in variable separable form. So it is something, these are the limits for y we consider, these are the limits for x. So y is equal to 0 to 1 with respect to y first. So I write down this as dy divided by root of 1 minus y square, and x is equal to 0 to 1 dx. So this is called variable separable form. Sorry, it is 1 upon root of 1 minus x square into dx. So this is variable separable form. So I will write down this as x from 0 to 1, and integration of this part, it is sine inverse of y, limits applied 0 to 1, and this is 1 upon root of 1 minus x square into dx. So if you apply the limits here, x from 0 to 1, so upper limit is 1, lower limit is 0. So sine inverse of 1, it is pi by 2, minus sine inverse of 0 is 0. So it is dx upon root of 1 minus x square. Now I simplify this further. It would be pi by 2, I take it outside, limits x from 0 to 1, 1 upon root of 1 minus x square into dx. Now integration of this, again it is sine inverse x, limits applied 0 to 1, so pi by 2, sine inverse 1 minus sine inverse 0, so value of this, it is pi by 2, and this is also pi by 2 minus 0, so answer is pi square upon 4 is the value of this integral. So likewise we can here evaluate some more integrals of this particular type. These are elementary problems on double integration. So next is second problem, evaluate x is equal to 0 to 1, evaluate the integral 0 to 1, y is equal to 0 to root of 1 plus x square dx dy divided by 1 plus x square plus y square. Now if you observe this integral, so here y having the variable limits of y as a function of x, variable limits for y. Therefore we integrate with respect to y first, and then with respect to x. So we write down this in the form, let I is equal to the integral. We put in variable separable form x from 0 to 1. So with respect to y, the inner bracket 0 to root of 1 plus x square with respect to y divided by 1 plus x square plus y square, and then with respect to x. So this is called variable separable form. Now x is constant while integrating this. X is constant, so x from 0 to 1, y from 0 to, I consider this as m. This is constant, 1 plus x square is constant. So 1 plus x square I will consider this as say m square. So it is dy divided by, because this is temporarily constant, x is constant, 1 plus x square is constant. So I integrate this. This is equal to x from 0 to 1. X from 0 to 1. Integration of this 1 upon m tan inverse of y upon m, and limits applied 0 to m into dx. I apply the limits x from 0 to 1, 1 upon m. Upper limit is m, so tan inverse of m by n, it is 1 minus tan inverse of 0. Tan inverse of 0 is 0. So this is pi by 4. So I am getting this as x from 0 to 1. This is pi by 4, and this m now, it is root of 1 plus x square into pi by 2 into dx. So I simplify this further. This is equal to pi by 2. I take it outside, and integration of this is log of x plus root of 1 plus x square, and limits applied 0 to 1. So I apply the limits and get the value pi by 4. Tan inverse 1 is pi by 4, not pi by 2, pi by 4. And you are getting this log of 1 plus 1 root 2 minus log of 0 if you apply 0, and this log 1 you are getting. Log 1 or ln, natural log to the base e. So this value is 0. So you are getting your answer pi by 4 log of 1 plus root 2 is the value of this double integration. So this is the technique of evaluating double integral with respect to y. First, because y having variable limits. Now similarly, next example, show that integral 0 to 1 minus y, x raised to m minus 1, y raised to m minus 1 dx dy. This is equal to gamma m gamma n upon m plus n gamma m plus n. So you have to evaluate this integral. So these are the limits for x, actually x as a function of y. These are the limits for x. So if x having variable limits, we integrate with respect to x first. So solution for this, let I is equal to the LHS side integral, y is equal to 0 to 1, x is equal to 0 to 1 minus y, and x raised to m minus 1, y raised to n minus 1 dx dy. I put it in variable separable form, x having variable limits, so with respect to x first, then with respect to y from 0 to 1. So I take y raised to, because y is constant outside the sign of first integral, x is equal to 0 to 1 minus y, and here x raised to m minus 1 into dx and then dy. So this is called variable separable form. First with respect to x, because x having variable limits, y is equal to 0 to 1, y raised to m minus 1. Now integration of this, it is x raised to m minus 1 plus 1 upon m minus 1 plus 1 and limits applied, it is 0 to 1 minus y into dy. So plus 1 minus 1 gets cancelled here. So you may be getting this as 1 upon m, I take it outside, y is equal to 0 to 1, x raised to m this, and y raised to m minus 1, so this y raised to m minus 1, and I apply the limits, this m is taken outside, apply 1 minus y, bracket raised to m minus 0 raised to m is the lower limit into dy. So upper limit minus lower limit. So this value is 0. So you may be getting this I is equal to the integral 1 upon m 0 to 1 y raised to m minus 1 minus y bracket raised to m into dy. Now we use beta function here, m minus 1. So I just add and subtract 1. So this is equal to 1 upon m by basic integral of beta of m. This is m and this is m plus 1. 1 minus y x raised to n minus 1. I'm sorry. This is n minus 1. N minus 1. This is n and raised to n over here. So it is n plus 1 minus 1. So beta of m n plus 1. Beta of m n plus 1. So by relation between beta and gamma function, that is beta mn is equal to gamma n upon gamma m plus n. Gamma n plus 1 divided by gamma m plus n plus 1. Now by reduction formula of gamma function, 1 upon m gamma m n into gamma, I think it should be en here, so it is en. So here it is n and this is also n, finally this is n. So n gamma m gamma n divided by, this is by reduction formula, m plus n gamma m plus n. So this n gets cancelled and you can write down this is as RHS. So this is final answer, gamma m gamma n m plus n gamma m plus n. Next example on this, fourth one. Next example, evaluate 0 to 1 integral 0 to x e raised to y by x into dx dy. So you have to evaluate this. Let I is equal to the integral I 0 to 1 0 to x e raised to y by x dx dy. Now if you observe here, so these are the limits for y as a function of x. So first to be integrated with respect to y, and these are the limits for x, first with respect to y and then with respect to x. That is what the approach to evaluate this integral. X from 0 to 1, now I put it in variable separable form, y is equal to 0 to x e raised to y by x into dy and then with respect to x. So this is called variable separable form. Now we integrate this with respect to y, keeping x as a constant, means 1 by x is constant. 1 by x is constant. So you are getting x from 0 to 1, integration of this y upon x divided by 1 by x, and limits applied 0 to x and dx. So that is what the integration in bracketed part. So I am getting this next step 1, this is x actually, and I apply the limits. If I apply the limits, e raised to x by x minus e raised to 0, so dx. So I simplify this. This is equal to x from 0 to 1, x from 0 to 1. So if you observe here, this is e x into e minus 1 into dx. So if you observe this, e minus 1 is outside, it is constant, and x from 0 to 1, it is x dx. Now if you observe this, e minus 1, this integration of x square divided by 2, limits applied 0 to 1. So e minus 1 divided by 2, I apply the limits 1 square minus 0 square. So this is e minus 1 divided by 2 is the value of this integral. So the next example on this. So these are the elementary examples on this. Next example, that is evaluate the integral 0 to 1 I is equal to 0 to 1, y is equal to 0 to x dx dy, check the time, dx dy divided by how many minutes left? 15. 15. Dx dy divided by x square plus y square. Okay, so say this. Now here solution, limits are y having variable limits. Let I is equal to the integral. It is x from 0 to 1, y from 0 to x. With respect to y first, naturally, because y having variable limits, x square plus y square into dx, and then with respect to x, y having variable limits. With respect to y, x as a constant. So you are getting x is equal to 0 to 1. So integration of this, tan inverse of y upon x, limits applied y 0 to x into dx. So you get this as x from 0 to 1, you apply upper limit, tan inverse x upon x minus tan inverse 0. Tan inverse x upon x, it is 1. So tan inverse 1 is pi by 4, x from 0 to 1. So this is pi by 4, tan inverse 0 is 0 dx. So this is equal to pi by 4 x from 0 to 1 into dx, or this is equal to pi by 4. If you apply the limits, x integration of 1, it is x 0 to 1. So the answer is pi by 4. Now in some cases limits are not given, you need to find limits of integration. So let us see that type of the problems. Evaluate Next example, evaluate the double integral r x plus y into dx dy, where r is domain bounded by x is equal to 0, y is equal to 0, x plus y is equal to 2. Domain bounded by x is equal to 0, x plus y less than or equal to 2 or is equal to 2. Solution, let I, now here limits are not given. You have to find out the limits. Region you have to sketch and you have to find out the limits. Let I is equal to the integral. I call this as r x plus y into dx dy, where r is domain bounded or region bounded, x is equal to 0, x plus y less than or equal to 2. Now if you observe, it is as shown in the figure. We try to locate this region. So this is x-axis, this is y-axis, this is origin. X-axis means y is equal to 0, y-axis means x is equal to 0, and it is this line. So this is located, x plus y is equal to 2. Now this line x plus y is equal to 2. For y is equal to 0, x is equal to 2. For x is equal to 0, y is equal to 2. Means line passing through 2, 0 and 0, 2, 0 and 0, 2. So this is the line. So this is line x plus y is equal to 2. So region bounded by this x, in fact greater than or equal to 0, y greater than or equal to 0. So this is region bounded by. This is the region of integration, or it is sometimes called domain of integration. This region of integration. Now to find limits for this, this is point A, this is point B. OAB is the region of integration. Now, how to get the limits? That is rather important part here. Now, to find limits, it's very usual all the time. We consider a vertical or horizontal strip in the region of integration or line in the region of integration. I encircle where the region start and I encircle where the region ends. So at this particular point, this point is P, this point is Q. At P, y is equal to 0. Y is equal to 0 at P, and at Q, it is boundary of this straight line, means y varies according as x. So 2 minus x. 2 minus x at this particular point, because y depends on x. So y as a function of x, y is equal to 2 minus x. And you have to move this straight line from x is equal to 0 to x is equal to 2. So limits for x is equal to 0 to x is equal to 2. So this is the way we find out limits. You consider vertical strip. You can consider horizontal strip also there. So you are getting different set of limits, but the value of the double integral would be same there. So I consider this as expression number 1. I insert the limits there. I is equal to from 1, I is equal to the integral. I put the limits there, these limits. So this is actually for, if you consider the vertical strip or the line of width dx. Similarly, if you consider horizontal strip, you can consider here, because this is regular. At this particular point, x is equal to 0. At this particular point, for x is equal to 0, 2x is equal to 2 minus 1. And you have to move this strip horizontally, vertically, from y is equal to 0 to y is equal to 2. Means, so you can consider this also. So you are having option. This is to be considered for the vertical strip. This is for the horizontal strip. These are the limits you are getting for the horizontal. Now here you need to integrate with respect to y first, because y having variable limits. And here in the second case you need to integrate with respect to x first, because x having variable limits there. So I consider these limits. Y is equal to 0 to 2 minus x, and x is equal to 0 to 2. So x plus y dx dy. Now here you need to integrate with respect to y first, with respect to y first, with respect to x first. Now we integrate this. X is equal to 0 with respect to y, means the variable separable form is y is equal to 0 to 2 minus x. X plus y, x plus y, x plus y into dy. X plus y into dy, and then with respect to x. So with respect to y first, keeping x as a constant, so x is equal to 0 to 2, and with respect to y, means x is constant. So x into y, integration of 1 is y plus y square by 2, and limits applied 0 to 2 minus x. 0 to 2 minus x. For y, we apply the limits. So it is something x from 0 to 2. So if you apply the limits, x into 2 minus x plus y, it is 2 minus x bracket square upon 2, and this is to be integrated with respect to x. So this is equal to x 0 to 2. So I just simplify this, 2 minus 2x minus x square plus 2 minus x bracket square upon 2, and to be integrated with respect to x. So I integrate this. This is 2 times integration of x square by 2 minus x cube by 3 plus integration of this 2 minus x bracket cube divided by 3 minus 3 into 2. So you are getting this in the form simplification, and getting the answer for this. It would be 2 gets cancelled here, and limits applied here 0 to 2. 0 to 2 is the limit application. So we get this as x square minus x cube by 3, x cube by 3 minus 2 minus x bracket cube divided by 6, and limits applied 0 to 2. So this is equal to, if you simplify this, upper limit minus lower limit, so it is 2 square minus 2 cube divided by 3 minus here 2 minus 2, it is 0 you are getting, and for the lower limit minus, it is 0 0 here 0 0 minus this thing 2 minus 0 means minus 2 cube divided by 6. So something like this. If you simplify this, then this would be, it is 4 minus 8 by 3 minus plus here 8 by 6. Now if you simplify, you are getting the final answer for this. So it would be something, it is 12 minus 4 by 12 minus 8 means 4 by 3 plus 8 by 6. 8 by 6 means, I'm sorry, it is 4 by 3. So this is equal to 8 by 3 is the final answer for this. So the next example on double integration, if limits are not given, evaluate double integral r dx dy divided by root of a square minus x square minus y square over the positive quadrant of the circle. Now if you observe this integral, so we need to find out limits. Let I is equal to the integral double integral r dx dy divided by root of a square minus x square minus y square. Let I is equal to this integral, where r is the positive quadrant of the circle, x square positive quadrant of circle, x square plus y square is equal to a square. This is circle with center at origin and radius is a. So I will try to show the positive quadrant of this circle. It is something like this. So this is positive quadrant. This is positive quadrant of the circle. This is x-axis. This is y-axis, and this is origin. So this point is a0, radius a, and center at 0, 0 of this circle. So x o x dash, y o y dash. So this is positive. This point is 0 a. Now we have to find out limits for this. This point is a. This point is b. So OAB is the region of integration. OAB is the region of integration. Now to consider the vertical strip or line in the region of integration, or so I encircle where the region start, I encircle where the region ends. So at this particular point, so this is boundary of the circle, x square plus y square is equal to a square. Now at this particular point, that is lower end, at P point, suppose this point is P, this point is Q. At P, y is equal to 0. At Q, y is equal to, because it is boundary of the circle, so y is equal to root of a square, positive square root in the positive quadrant. So root of a square minus x square. And you have to move the line, because this y-axis, x is equal to 0 to x is equal to a. So you have to move this line from this position to this position. From this position to this position, x is equal to 0 to x is equal to, see, horizontally, from x is equal to 0 to x is equal to a. Now you can take horizontal strip also, horizontal line also. You encircle here, encircle here, x is equal to 0, x is equal to root of a square minus y square, and vertically you have to move from y is equal to 0 to, you are getting another set of the limits. No need of considering, we consider this set of the limits for the region of integration. Now from 1, I call this is 1, from 1, I is equal to the integral, I is equal to the integral, y is equal to 0 to root of a square minus x square, x is equal to 0 to a dx dy divided by root of a square minus x square minus y square. Now y having variable limits, so we integrate with respect to y first and then with respect to x. If vertical strip, you have to integrate with respect to y first, and if it is horizontal strip, you need to integrate with respect to x. So this is to be kept in mind all the time. So it is this x from, I just put x is equal to 0 to a, I consider this as y is equal to 0 to m, I will consider. So I put this in variable separable form with respect to y first, divided by root of a square minus x square, it is m square minus y square into dx. So this is called variable separable form. M I have considered m square is equal to a square minus x square. This is temporary substitution I have taken because while integrating with respect to y, x is constant. So a square minus x square is constant. So integration of this x from 0 to a, I integrate this. This is sine inverse y upon m and limits apply 0 to m and then dx. So I integrate this x from 0 to a and upper limit, it is m is this actually. So you are getting this sine inverse m upon m is 1, sine inverse 0 is 0 into dx. So you are getting this as sine inverse 1 is x from 0 to a, sine inverse 1 is pi by 2 minus 0 into dx, and we simplify this. This is equal to pi by 2 is outside, it is constant, x from 0 to a into dx, and this is equal to pi by 2 x limits from 0 to a. So this is equal to pi a divided by 2 is the value of this integral, pi a divided by 2. Now next is next problem. Evaluate double integration r dx dy divided by x raised to 4 plus y square, x raised to 4 y square, where r is region bounded by y is greater than or equal to x square, x greater than or equal to 1. So if you observe this solution, let I is equal to the integral, this integral, double integration r dx dy divided by x raised to 4 plus y square. Now if you observe here, this is r actually. So if you observe, this is parabola and this is straight line. So r is this region, y is greater than x square and x greater than 1. So I try to locate this region of integration. Y is equal to x square is parabola, symmetrical about y axis, y is equal to x square, this is parabola, y is equal to x square, and this is the region y greater than x square. So and this one x greater than 1, x is equal to 1, we find the point of intersection, y is equal to x square and x is equal to 1. If I put x is equal to 1, y is equal to 1, so point of intersection of parabola and the straight line, it is 1, 1. X is equal to 1, y is equal to 1 square, so y is equal to 1. 1, 1 is the point of intersection. So this is region bounded by this. So this would be the region, and this is origin. This is y is equal to x square, y greater than x square. So this is region bounded by the straight line and the parabola. X greater than 1 means this region is here. So this is the portion x greater than 1. X greater than 1 because this point is 1, 0, x greater than 1, and y greater than means it is this portion. So this is region. Now I draw the vertical strip here, vertical line in the region of integration to find out the limits. So I encircle lower where the region start, y is equal to vertical means y is equal to x square. Now it ends infinite region, so y is equal to infinity, and you have to move the strip from x is equal to 1 to x is equal to infinity. So these are the limits of region R of integration. So I just take it from here from 1 I is equal to, it is this y is equal to, with respect to y first we have considered vertical strip, y is equal to x square to infinity and x from 1 to infinity. And with respect to y means dy divided by 1 x raised to 4 plus y square, and then with respect to x. So integration of this with respect to y, x is constant, x from 1 to infinity. So integration of this 1 upon x square, because x raised to 4 you can write x square square. Now we use the formula tan inverse of y upon x square, and limits applied, it is x square to infinity into dx. So you get this as x from 1 to infinity 1 upon x square. I apply the limits, upper limit tan inverse infinity pi by 2 minus tan inverse of 1, it is pi by 4. So into dx, so pi by 2 minus pi by 4, it is pi by 4, limits 1 to infinity, this is 1 upon x square into dx. Now integration of this, x raised to minus 2 plus 1 upon minus 2 plus 1 means pi by 4 minus 1 upon x, and limits applied 1 to infinity. So minus pi by 4, upper limit, it is infinity, is 1 upon infinity minus 1. So this is 0. Minus 1 means answer is pi by 4. So that is value of this double integration over this region R. See how to transform double integral into polar coordinates, polar form, and why it is required to transform double integral into polar coordinates or polar form. The reason is that mostly the integral where the integrand f of xy, it is not possible to find out the value in terms of x and y, integral value in terms of x and y. In that case, normally the square root of circles or ellipse, this type of the integrand, if it is there, function is there, we normally use to transform into polar coordinates. So that is the only reason where it is not possible to transform this integrand, this not possible to integrate this integrand by the traditional method with respect to x or with respect to y. So we transform into polar coordinates. As usual, you know, polar coordinates, x is equal to r cos theta, y is equal to r sin theta, x square plus y square, theta tan inverse y by x. And if it is required to transform this double integral with r is the domain or region of integration into polar coordinates. So what we do, we use these substitutions there, the necessary substitutions, and for this region also it is something else. It is bounded by two curves, r is equal to f1 theta, 2r is equal to f2 theta, these two curves there, and the straight lines, theta is equal to alpha, theta is equal to beta, these straight lines there, theta is equal to alpha, theta is equal to beta, and a, b, c, d is the region of integration. Here bounded by these two curves and these radial lines there, theta is equal to alpha and theta is equal to beta. So this region, if you observe, R, it is domain or region of integration. Now we transform this double integral into polar coordinates. It is this. So this from 1 double integral R f of x is equal to r cos theta I have put, y is equal to r sin theta, then dx dy is r d theta dr. So normally this is function of r, this thing. So this thing function of r, this whole thing. So I will consider this as capital F of r theta, where r is this region actually that is located in the figure or in the diagram. R is equal to f1 theta, r is equal to f2 theta, theta is equal to alpha, theta is equal to beta. This is customary to denote the region of integration in the polar coordinates. So what we do here to find out limits now, look at the limits. So to find limits, we draw a strip OPQ, radial strip actually, in this region of integration OPQ, where r varies from point P to point Q. At this particular point, it is boundary of this particular curve. So at P, r is equal to f1 theta. At Q, r is equal to f2 theta. That is boundary of this. So with this radial strip, we rotate this strip in this direction. So that is what I have shown here. So we rotate in this direction from where to where? So till it is merging with the line theta is equal to alpha to theta is equal to beta. So that is what the limits for r and theta you are getting there. So r I will substitute theta 1 to theta 2, then the theta I will substitute alpha to beta, f of r theta d theta dr. Now here if you observe, r having variable limits are as a function of theta. Variable limits are as a function of theta. So we integrate, we put it in variable separable form with respect to r first, keeping theta as a constant. So this is to be integrated with respect to r first. If r having variable limits, normally r having variable limits all the time. So if it is there, then we all the time integrate with respect to r, keeping theta as a constant, and then with respect to theta, because this is, if you try to integrate this, theta is constant, so you are getting function of theta, and this is to be integrated with respect to theta, you are getting phi of beta minus phi of alpha. If you take primitive of f of theta to be phi of theta, so phi of beta minus phi of alpha is the value, or this is procedure to transform this Cartesian double integral into polar double integral. So let us see some examples on this. As I said, there is remark how to transform, why to transform double integral into polar. Normally, if the region of integration is circular or elliptical, it is always convenient, it is always handy, it is always easy to transform the double integral into polar coordinates, and easy to get the value of double integral by transforming into polar coordinates. So let us see examples. Evaluate, first example on this, evaluate the double integral, r xy dx dy double integral xy dx dy over the positive quadrant, of circle, x square plus y square is equal to 4. X square plus y square is equal to 4 by transforming into polar coordinates. So you can transform this into polar coordinates by transforming into polar coordinates. So let us see what to do with this to transform into polar coordinates. So let I is equal to the integral, it is this double integral r xy dx dy. I call this is expression number 1, where r is the quadrant of the circle, it is positive quadrant of circle x square plus y square is equal to 4. This is circle having center at 0, 0, radius 2. So I will draw this circle here. It is something like this. So this circle, x axis, this is y axis, this is origin, and over this is region of integration r, positive quadrant of the circle. So radius is 2, so this point is 2, 0, this distance is 2, and so on. This is theta is equal to pi by 2, this is theta is equal to 0. Now I have to write polar equation of the circle. So this circle, it is r square is equal to 4. So r is equal to 2 is the polar equation of the circle. So to transform, put x is equal to r cos theta, y is equal to r sin theta to transform into polar, and naturally x square plus y square, if you work out, it is r square, and dx dy, it is defined as dA by xy upon dA by r theta d theta dr. It would be something, all the time it is taken as r d theta dr because value of the Jacobian, it is r there. So we transform this integral. Now, so this is the region of integration. This is A, this point is 0 to, means this is B here. OAB is the region of integration. Now to find limits for this. So limits for this, we draw a always radial strip from the pole where r is always equals to 0, and at this particular point it is boundary of the circle r is equal to 2. At this particular point r is equal to 2, it is boundary. This is equation of circle, and you have to move this strip in the direction anti-clockwise direction. So radially r varies from r is equal to 0 to r is equal to 2, and theta is in anti-clockwise direction. This is theta is equal to 0 position, and this is theta is equal to pi by 2 position. So you have to move this strip from this position to this position, means theta is equal to 0 to theta is equal to pi by 2. So these are the limits for region R. So we get it transformed from 1 I is equal to, I just put the limits and transform into polar. R is equal to 0 to 2, theta is equal to 0 to pi by 2, and x is equal to r cos theta, y is equal to r sin theta, dx dy is, as usual I said right now, it is r d theta dr. So I simplify this. This is equal to theta is equal to 0 to pi by 2. I put this in variable separable, r, it is r cube, sin theta cos theta. I simplify a little bit. So sin theta cos theta, r is equal to 0 to 2, r, it is r cube dr, and then to be integrated with respect to theta. So this is equal to theta is equal to 0 to pi by 2, sin theta cos theta, and integration of this, it is r raised to 4 divided by 4, and limits applied 0 to 2 d theta. So you are getting this as 2 raised to 4 divided by 4, and theta 0 to pi by 2 sin theta cos theta. So I multiply and divide by this sin theta cos theta divided by 2. So you are getting into d theta, and further simplification for this, 2 raised to 4 is 16 upon 4, or 2 raised to 4 16 upon 8, it is 2 times 0 to pi by 2 sin 2 theta d theta. So integration of this is equal to 2 times minus cos 2 theta divided by 2. Limits applied, this 2 gets cancelled, 0 to pi by 2. So this is equal to minus inside the bracket cos pi minus cos 0. So cos pi, it is minus 1, cos 0 minus 1, minus 2. So value of this integral is 2. So this is the way you can just evaluate these integrals by transforming into polar coordinates. So this is first example. Second problem. Second problem. Evaluate the integral the integral 0 to 2 times a 0 to 2 times a 0 to root of 2ax minus x square plus y square plus y square dx dy by transforming into polar coordinates by transforming into polar coordinates polar coordinates. So let us see what to do with this solution. If you observe this, so it is rather complicated. Region, limits, boundaries. So we transform and circle. In fact, it is given, let I is equal to the integral 0 to 2 times a 0 to root of 2ax minus x square plus y square dx dy. So if you observe this, so this is function of x, so naturally these are the limits for y here and these are the limits for x. So we just list out the boundaries here. By Cartesian it is rather complicated. So y is equal to 0, limits y is equal to 0, y is equal to root of 2ax minus x square, x is equal to 0, 2x is equal to 2 times a. Now if you just square this, y square is equal to 2ax minus x square. Y square 2ax minus x square, or you can write down this as x square is taken on this side, x square plus y square is equal to 2 times x. So this is circle with center at 0, 0, A0 and radius is A. This is circle, or you can write down this in this particular form, x minus a bracket square. This is actually circle touching to y-axis. This is equal to a square. If you simplify this, taking on this side x square minus 2x plus and so on. So this is circle with center at this particular point. So it would be something like this. This circle, it is this. So this is center at A0 and radius A. So naturally this point is 2 times A0. So this is origin. This is origin here. So this is y-axis, this is x-axis. And if you observe, y is equal to 0. This is the strip actually. This is y is equal to 0 or the straight line. So at this particular point, y is equal to root of 2ax minus x square. This. And it is moved from x is equal to 0 to x is equal to 2 times a. That is what? This line here, limits for x. So we have to transform this. So this is region of integration. So this is region of integration from this particular point to this point, and this strip is moved from x is equal to 0 to x is equal to 2 times a. Now to transform into polar, we put this thing, take the strip always from the pole where r is always equals to 0. So this is boundary of x square plus y square is equal to 2 times x, the equation of circle. We transform this into polar, x square plus y square r square and 2 times a, it is r cos theta. So I simplify this, r is equal to 2 times a cos theta. This is standard equation in the polar form of the circle with center at A0 and radius is a. So at this particular point, r is equal to 2 times a cos theta. At this point, r is equal to at this particular point, r is equal to 0 to r is equal to 2 times a cos theta. These are the limits for r. On this radial strip, and it is to be moved in this direction. So this is the movement of the stick. This is the moment. So still it become tangent at this particular point. So theta is equal to 0 is this line to theta is equal to pi by 2. So these are the limits for theta. Theta is equal to 0 to theta is equal to pi by 2 in order to cover that complete region sweeping out by this radial strip. So it will go like this from theta is equal to 0 to theta is equal to pi by 2. Therefore, integral 1, I call this is what? From 1, so we get it transformed by the substitution as usual. X is equal to r cos theta, y is equal to r sin theta, x square plus y square r square dx dy. It is r d theta dr. Right now we have seen in the earlier example. So get it transformed. I is equal to the integral. So we get it transformed. R is equal to 0 to 2 times a cos theta with these limits, and theta is equal to 0 to pi by 2, and x square plus y square, it is naturally r square dx dy, it is r d theta dr. Okay, so we simplify this. This would be, as I said earlier, first to be integrated with respect to r and then with respect to theta. So I write down this as r is equal to 0 to 2 times a cos theta, 2 times a cos theta, and limits, if you observe, it is r cube dr, limits 0 to 2 times a cos theta and d theta. It is something like this. So we get theta is equal to 0 to pi by 2, and integration of this, it is r raised to 4 divided by 4, and limits apply 0 to 2 times a cos theta d theta. So this is equal to 1 by 4, I take it outside, theta 0 to pi by 2, and this is 2 times a cos theta bracket raised to 4, and lower limit its value is 0, did not be considered. This is 2 raised to 4, 2 raised to 4, it is 16 upon 4, limits 0 to pi by 2, 0 to pi by 2, and here a raised to 4 also there. It is cos raised to 4 theta d theta. So you are getting this is 4 times a raised to 4, 4 times a raised to 4 using reduction formula here, 4 minus 1 upon 4, 4 minus 3 upon 4 minus 2, and pi by 2 because it is even positive integer. So we simplify this, a raised to 4 multiplied by 3 by 4, then next is 1 by 2, and next is pi by 2. So we simplify this and see this 4 gets cancelled. So you are getting your answer 3 pi a raised to 4 divided by 4 is the correct answer for this. So this is value of this integral by transforming into polar coordinates. So we shall see one more example on this, transforming into polar coordinates, and hence evaluate. Let us transform this integral into polar coordinates and evaluate. So let us see one more example. Evaluate. Show that, problem number 3, show that double integral r x square y square upon x square plus y square, x square plus y square dx dy, this is equal to 65 pi by 16, where r is annulus between, r is annulus between the circles x square plus x square plus y square is equal to 4 and x square plus y square is equal to 9. So if you observe this circle with center at 0, 0, radius 2, this circle with center at 0, 0, radius is 3. So it is rather complicated to work out this problem by Cartesian coordinates if you observe. So we need to transform this into polar coordinates solution. So we transform into polar coordinates. Let I is equal to the integral, double integral r x square y square divided by x square plus y square dx dy. It is this. So where r, it is annulus of this. So region bounded by these two circles, x square plus y square is equal to 9. So straightway we take polar equation for this. R is equal to 2 and this is r is equal to 3. So we have seen center and radius of these circles. We just try to draw these circles here. It would be something like this. So these are concentric circles actually. So this is origin, this is x-axis, this is y-axis, and this is annulus. This is inner circle, x square plus y square is equal to 4, and this is outer circle, x square plus y square is equal to 9. In fact, it is r is equal to 3 and this one is r is equal to 2. So this is annulus between the circles, and this is r is equal to 0, this is theta is equal to 0, this is theta is equal to pi by 2, and so on. And so you need to draw a strip here. It is this. So this is OPQ. So region exists between these 2 points here. So here r is equal to 2, here r is equal to 3, and here r is equal to 0. So this is the strip OPQ, is the radial strip there. Now I call this as expression number 1. Transforming 1 into polar coordinates. So this is the region of integration or domain of integration, which is annulus between the circles x square plus y square is equal to 4 and x square plus y square is equal to 9. So from transforming double integral, transforming 1 into polar by putting x is equal to r cos theta, y is equal to r sin theta as usual, dx dy, this is equal to r d theta dr. So what happens here? R varies from r. For this region, r varies from 2 to 3. That is the limits for r, and theta varies from. So you have to move this strip this direction in order to cover the whole region. It is 0 to 2 times pi. Theta is equal to 0 to 2 times. Take the one round there. Theta is equal to 0 to theta is equal to 2 times pi. So I just got this then. From 1, I is equal to the integral. I just put the limits there. R is equal to 2 to 3. Then theta is equal to 0 to 2 times pi. X square y square. X square means r square cos square theta. From here, y square r square sin square theta divided by x square plus y square is r square. Dx dy is r d theta dr. So we simplify this, put it in variable separable in terms of theta and r. So it would be something sin square theta, I take it outside, cos square theta, I take it outside, and here r is equal to 2 to 3, and here it is r square get cancel from here r cube into dr into d theta. So I just simplify this further. 0 to 2 times pi sine square theta cos square theta, and this one r raised to 4 divided by 4 limits 2 to 3 into d theta. I apply the limits here. 1 by 4 I take it outside. 0 to 2 times pi sine square theta cos square theta, and here 3 raised to 4 minus 2 raised to 4 into d theta. So 3 raised to 4 is 81. This is equal to 1 by 4. 1 by 4, it is something like this. This is 81 minus 16, 2 raised to 4, and 0 to 2 times pi sine square theta. I will write down this as 2 times 0 to pi, 4 times 0 to pi by 2. By using the property of definite integral, sine square theta, cos square theta, d theta. I simplify this. This 4 may be getting cancelled here. So this is 65. What is this? We are getting 81 minus 16. This is 65. So you are getting this as the final answer. If you simplify, you may be getting it is 65 multiplied by. Now we are using reduction formula for this. It is 2 minus 1 in first bracket. Second bracket also it is 2 minus 1 divided by 4 minus 2, and multiplied by pi by 2. So if you simplify this, 65 pi divided by, this is 16, 4 into 2 into 2, it is 16. So that is what the answer for this problem. So this is the way you can transform double integral with some complicated integrand. So change of order of integration. Dear students, change of order of integration when it is required. Sometimes the given integral is not possible to find its value, or sometimes difficult to integrate in the given order. So we change the order of integration. So let us see what is change of order and how to evaluate such type of the integrals. So let us see one example over here. So change of order of integration. So change the order and evaluate the integral. The integral, it is given as 0 to infinity, 0 to x to infinity, e raised to minus y divided by y into dx dy. So you need to find value of this integral. Now if you observe, so these are limits for y here and these are the limits for x. So if you observe, you have been asked to integrate with respect to y first, keeping x as a constant. In fact, it is not possible, or it is rather complicated to integrate this with respect to y, because this is function of y, and easy to integrate with respect to x. So that's why it is required to change the order of integration. So here the limits are limits. So what? Let us see what it means, the changing the order of integration. So limits given here, y is equal to x, y is equal to infinity, then x is equal to 0, x is equal to infinity. So we sketch the region of integration for this limits here, and it would be something like this. So I just sketch the region here, x-axis, this is y-axis, this is origin. Now y is equal to x is this line, y is equal to x is this line, y is equal to x. to y is equal to infinity. Y is equal to x to y is equal to infinity. So this complete portion is there. This is y is equal to x, this point, and this point in this particular direction y is equal to infinity, and x varies from, this is x is equal to 0 and x is equal to infinity, means this complete quadrant, half quadrant, is the region of integration. Now changing the order means what actually? So you have to move the step from x is equal to 0 to x is equal to infinity. Now changing the order means you have to take the reverse step, reverse line. So I just take this. So at this particular point, I just note the values of x, because x varies or changes horizontally. So at this particular point, x is equal to 0. So by changing the order, x is equal to 0 to x is equal to y. X is equal to y, and you have to move the strip, this strip, vertically from this line y is equal to 0 to y is equal to infinity in order to cover. Means like this, you are just considering the lines there. We are collecting such a number of steps of width dy from y is equal to 0 to y is equal to 0 to y is equal to infinity. So these are the limits you got after changing the order of integration. These are original limits there. So with these limits you cannot integrate with respect to x, and it is difficult to integrate with respect to y. So we make the integral to integrate with respect to x, because it is easy to integrate with respect to x, and these are the limits there, and we just put these limits there. So I call this as expression number 1. This is integral I. So I just put these limits there and evaluate with these limits by changing the order of integration. So I put the limits there from 1 I is equal to the integral with new limits. It is x is equal to 0 to x is equal to y is equal to 0 to y is equal to infinity, with new limits e raised to minus y divided by y dx dy. Now here if you observe, we have to integrate, because x having variable limits we have made here. So with respect to x we have to integrate first, and then with respect to y. So with respect to x means I just take y is equal to 0 to infinity e raised to minus y divided by y, outside the sign, putting in variable separable form, and x is equal to 0 to y into dx and then dy. This is something like this. So with respect to x first, y is equal to 0 to infinity e raised to minus y divided by y. Now I integrate this, so it is x, limits applied, 0 to y dy. So this is equal to y from 0 to infinity e raised to minus y, and if you apply the limits, y minus 0 means simply y, and divided by y is there. So this y gets cancelled, and you are required to integrate this 0 to infinity e raised to minus y dy. So this is equal to e raised to minus y divided by minus 1 is the integration, and limits applied 0 to infinity. So minus, if you apply the upper limit, e raised to minus infinity e raised to 0. So this value 0 minus 1, so value of this integral, it is 1. So we change the order of integration and evaluate. So let us see more example on this, changing the order of integration and evaluating. I just go for one more example here. It is this second problem. change the order and evaluate. Change the order. Change the order of integration and evaluate. Evaluate. Change the order of integration and evaluate. So this is 0 to 1, 0 to 1, 0 to root of 1 minus x square dx dy, dx dy divided by 1 plus e raised to y into root of 1 minus x square minus y square, x square minus y square. Now here if you observe this, so this is function of y. These are the limits for y here, and these are the limits for x. These are the limits for x here. So you have been asked to integrate with respect to y first and then with respect to x. So what you are doing here, with respect to y, if you try to integrate, this is function of y, this is function of y, and the denominator. It is rather complicated to integrate this with respect to y, even impossible. So what we do in this case, and easy to integrate with respect to x. If you just observe this, you can integrate with respect to x, keeping y as a constant. This is already function of y, we can take it outside. So to integrate this with respect to x, we have to change the order of integration. We have to make the variable limits for x there to integrate with respect to x. And it is possible only by changing the order of integration. So solution, I call this is our solution. Limits here, limits of integration. Limits y is equal to 0 to y is equal to root of 1 minus x square, and x is equal to 0 to x is equal to 1. So I simplify this, squaring on both sides for this boundary 1 minus x square, or this implies y square plus x square is equal to 1. This is circle with center at 0, 0 and radius 1. This is circle with center at 0, 0, radius 1. I draw this circle here. It would be something like this. This is x-axis, this is y-axis, and this is normal circle with center at 0, 0, radius 1 there. And if you observe here, these are the limits over the strip or the line. So y is equal to 0 to y is equal to, so strip or line you can take. So this is boundary of the circle, y is equal to root of 1 minus x square, and this strip, it is moved from x is equal to 0. So x is equal to 0 means y axis to x is equal to 1 means y is equal to 0. So this portion, and it is moved from x is equal to 0 to 1. So this is the region of integration. Now to change or reverse the order of integration, we take the opposite strip here. So if you observe this strip at this particular point, at this particular point, at this particular point, here x is equal to 0 and this is boundary of the circle. So this is x is equal to 0 and this is x is equal to root of 1 minus y square. 1 minus y square. So these are the new limits here. After changing the order of integration, x is equal to 0 to x is equal to root of 1 minus y square. And you have to move this strip vertically from y is equal to 0 to y is equal to 1. Y is equal to 0 to y is equal to 1. So these are the limits after changing the order of integration. In order to integrate this, or we are making to integrate this with respect to x. Now with these limits you can integrate with respect to x. So therefore I is equal to the integral. This will take the form with new limits. X is equal to 0 to root of 1 minus y square. Y is equal to 0 to 1. Then I write down this as d x dy divided by 1 plus e raised to y into root of 1 minus x square minus y square. Now with respect to x we have to integrate, so I take this outside. So y is equal to 0 to 1, and I just take 1 upon 1 plus e raised to y, it is constant. So x is equal to 0 to root of 1 minus y square dy upon dx upon root of 1 minus x square minus y square into dy. So like this, we just integrate this part here. This is equal to y is equal to 0 to 1, 1 upon 1 plus e raised to y. I take this as, for the simplicity, constant. Root of 1 minus, this is EM say dx upon, so 1 minus x square, 1 minus y square, it is that naturally it is m square minus x square, because 1 minus y square I take it is m square. So for the simplicity, or m is equal to, naturally it is root of 1 minus, this is temporary substitution I have taken in order to avoid the complications. So I just integrate this. This is y is equal to 0 to 1, 1 upon 1 plus e raised to y. And integration of this, it is sine inverse of x upon m, and limits applied 0 to m into dy. I apply the limits. This is equal to y is equal to 0 to 1, 1 upon e raised to y, and this is sine inverse 1. It is pi by 2, sine inverse 0 is 0, and dy. So this is equal to pi by 2, 0 to 1 dy upon 1 plus e raised to y. Now we have to integrate this. 0 to 1 e raised to y dy upon 1 plus e raised to y. So simple integration. This integration we have to carry out. This is pi by 2, 0 to 1 dy upon 1 plus e raised to y. Dy upon 1 plus e raised to y. I take e raised to y outside, so I can write down this in the form 0 to 1, or multiply and divide by e raised to minus y, numerator and denominator. So it is e raised to minus y dy, and here it is e raised to minus y plus 1 minus y e raised to 0. So likewise, now I integrate this. So this formula I am using, integration f dash divided by f. So derivative of this is minus, so minus pi by 2. So I can write down this as minus pi by 2 log of 1 plus e raised to minus y, and limits applied 0 to 1. So you can simplify this. This is equal to minus pi by 2 and upper limit minus lower limit 1 if you are putting 1, log of 1 plus e raised to minus 1 upper limit minus lower limit minus log of 1 plus e raised to 0, it is 1. So you are getting this as minus pi by 2 inside the bracket log of 1 plus, to simplify this, 1 plus 1 upon e minus log 2, something like this. So you can simplify this, minus pi by 2 inside the bracket. This is log of e plus 1 divided by e minus log 2, or you can simplify this as minus pi by 2 inside the bracket log of e plus 1 divided by 2 times e. So this is final answer for this problem. So this is changing the order of integration. You can change the order of integration and evaluate. So let us see One more example here. Problem number 3. Is show that 0 to 1 value of the double integration, 0 to root of 1 minus y square cos inverse x divided by root of 1 minus x square minus y square root of 1 minus x square dx dy. This is equal to pi cube divided by 16. Pi cube divided by 16. Now, if you observe this, so these are the limits for x and these are the limits for y here. So if you observe, in the given order, it is rather complicated to integrate with respect to x first. So you have to make this integral to integrate with respect to y by changing the order of integration. So limits would be this, limits x is equal to 0, x is equal to root of 1 minus y square, y is equal to 0 to y is equal to 1. So if you observe, again the same thing, you are getting x square is equal to 1 minus y square. So x square plus y square is equal to 1. This is again circle with center at 0, 0 and radius is 1. Center at 0, 0, radius is 1. This is circle, x-axis, this is y-axis, this is origin, and so this is horizontal strip, x is equal to 0 to x is equal to, this is boundary of x is equal to root of 1 minus y square. And you have to move the strip from y is equal to 0, means y is equal to 0 to y is equal to 1. So it is something. This is y is equal to 1. So this is region of integration, origin. Now to change the order, we take, here it is taken as horizontal, we have to take vertical strip in the region of integration, where we just encircle from where the strip start, where the strip end. So lower end, it is y is equal to 0 and upper one, it is y is equal to root of 1 minus x square. It is boundary of the circle in the first quadrant, and x varies. So you have to move this because coordinate of this point is 1, 0 and this one is 0, 1. So x from 0 to x is equal to 1. X is equal to 0 to x is equal to 1. So these are the limits after changing the order of integration. Now what I do here, I just consider this integral, consider the integral, and we try to integrate in this order by changing. Consider I is equal to this integral. I just take the limits, new limits I put there, y is equal to 0 to root of 1 minus x square. After changing the order, x is equal to 0 to x is equal to 1, and here cos inverse of x divided by root of 1 minus x square minus y square root of 1 minus x square into dx dy. Now with respect to y first, keeping x as a constant, we have made it. So I just take terms of x outside, 0 to 1, so cos inverse x divided by root of 1 minus x square, I take it outside. And here y from 0 to root of 1 minus x square dy upon root of 1 minus x square minus y square into dx. It is this. So again I consider this as some constant. So I consider this as x is equal to 0 to 1 cos inverse x divided by root of 1 minus x square. So this is m 0 to m dy upon root of m square minus y square. This is temporary substitution we have taken because x is constant there. So 1 minus x square is equal to m square, or root of 1 minus x square is equal to m. So this temporary substitution we have taken. So x from 0 to 1 cos inverse x divided by root of 1 minus x square. So this is sine inverse of y upon m integration and limits applied 0 to m into dx. Now this, as usual, sine inverse m upon m is 1. So it is x from 0 to 1 cos inverse x divided by root of 1 minus x square. This is sine inverse m upon m 1 sine inverse 0. It is pi by 2. So this is pi by 2 minus 0. So you are getting, I take this pi by 2 outside, 0 to 1, or I just write down 0 to 1 cos inverse of x divided by root of 1 minus x square into pi by 2 minus 0 into dx, because sine inverse 0 is 0, sine inverse 1 is pi by 2. Now we have to integrate this. The next step to integrate and get the final answer would be something like this. So we integrate. This is pi by 2, 0 to 1 cos inverse x divided by root of 1 minus x square into dx. So we use substitution, put cos inverse x is equal to t, therefore minus 1 upon root of 1 minus x square dx is equal to dt, and limits would be, you are getting pi by 2 to 0, new limits. So you are getting this as pi by 2, 0 to pi by 2 to 0, and this is t, cos inverse x is t, and this is minus dt. So you are getting this as minus pi by 2 or plus pi by 2. I just change the limits here, and this one t dt. So I integrate this pi by 2 t square divided by 2, limits applied 0 to pi by 2. So this is equal to pi by 4, and this one pi by 2 bracket square minus 0. So you are getting pi cube divided by 16 is the value of integration. So this is the way you can change the order of integration and evaluate the certain integrals. That's all. Dear students, now we move to applications of double integration. So if you observe, there are 3 to 4 applications of double integration. The first one is area, second application center of gravity, next application moment of inertia, and next one is center of pressure. So like this we are having important applications of this. Sometimes you are using double integration to find out mass also. Mass of a lamina, center of gravity of the plate, and so on. So first application is area. This is key application actually. So area double integration r dx dy is equal to double integration r d theta dr. So uh, this is formula area double integration r dx dy in Cartesian coordinates. This is Cartesian, means the equation given in Cartesian form x and y. Then you can find out area by this formula. If the equation given in polar form, then you are using this formula to find out area. Let us see quickly some examples here. Find area of circle x square plus y square is equal to a square by using double integration. We know area of the circle is pi a square. Okay, so let us use double integration to find out area. So this circle, you know, it is something like this. This circle. So having center at 0, 0 and radius is a. This circle. So this is center, radius a. Now to find out area of this circle, and that is pi a square. So I can find out area of this part of the circle located in positive quadrant and make it 4 times. So area of the circle is equal to 4 times area dx dy. It is something like this. Okay, area of OAB. This point is A, this point is B, the quadrant OAB. Now I find out the limits. So for limits, as usual, we draw a vertical or horizontal strip. Here this line or strip y varies vertically. At this particular point, you know, y is equal to 0. At this particular point, it is boundary of this circle. So y is equal to, from this equation, it is root of a square minus x square. So these are the limits for y. So limits are important all the time. Y is equal to root of a square minus x square. And you have to move the strip from merging to this line to this line. So this is x is equal to 0. So limits for x 0, and here this line is x is equal to a parallel to y axis. So these are the limits there. So if you take horizontal strip, then x from 0 to x equal to root of a square minus y square, y is equal to 0 to a, like this. So I just put the limits there. 4 times y is equal to 0 to root of a square minus x square, x is equal to 0 to a dx dy. So y having variable limits, therefore we integrate with respect to y first, and if you take horizontal strip, then we integrate with respect to x first. So it does not make any difference there. So you need to here integrate with respect to y. So I just put in variable separable form here, root of a square minus x square into dy, and then with respect to x. So I integrate this bracketed part. So 4 times x from 0 to a, and here integration y limits 0 to root of a square minus x square into dx. So you are getting this as 4 times 0 to a integration. This is root of a square minus x square minus 0. Now we have to find integration of this. So integration of this is 4 times, if by the formula it is x by 2 root of a square minus x square plus a square by 2 sine inverse x by a, and limits applied 0 to a. So if you apply the limits, upper limit, this is 0, this is 4 times. So here it is 0 because a square minus a square 0 plus a square by 2 sine inverse a by a means 1, sine inverse 1. And lower limit, if you observe 0, this is 0, sine inverse 0 also 0, need not be considered. So you are getting this as 4 times a square divided by 2 into pi by 2. So this 2, 4 gets cancelled. Pi a square is area of the whole circle. So this is the way you can find out area by using double integration. Now this is in Cartesian. The same area, suppose you would like to find in polar. Then what happens? See, the formula, you are having choice here to find out area in polar coordinates. So area in polar you can find out. So you transform that equation into polar, r or OAB r d theta dr. Now what you are doing here, see, to find L polar, so you have to convert this equation into polar, equation of circle. So it is naturally r square is equal to a square, or r is equal to a is the equation of circle in polar coordinates. Now in polar we take the radial strip here, okay, and here r is equal to 0, here r is equal to a. So these are the limits for r is equal to 0 to r is equal to a, and you have to move this radial strip in this anti-clockwise direction in order to cover this quadrant of the circle. So we make it 4 times here also. So this line is theta is equal to 0, in fact it is x-axis, and this line is theta is equal to pi by 2. So limits for theta 0 to pi by 2. So in the polar coordinates, answer would be same there. R is equal to 0 to a, theta is equal to 0 to pi by 2, r d theta dr. Now I integrate with respect to r first, limits are constant, so you can integrate with respect to r theta, it does not make the difference. R is equal to 0 to a, r dr, and then d theta. So integration of this, 4 times 0 to pi by 2, r square divided by 2, limits applied, 0 to a into d theta. So this is equal to, so 2 2s are 4, so 2 times 0 to pi by 2, and here a square d theta. So you are getting this 2 times a square 0 to pi by 2 d theta. This value is naturally pi by 2, 2a square into pi by 2, because theta limits pi by 2 to 0 means you are getting pi a square. So likewise you can find out value or the area by using double integration. In Cartesian or in polar, it does not makes the difference. You can convert the equation into polar or in Cartesian. You can get by the requisite formula to find out area. Now next example, second example, find area of the cardioid area bounded by cardioid r is equal to a 1 plus cos theta by double integration. So you have to find area of this cardioid bounded by this cardioid by using double integration. Solution, area, so this is polar curve. R is equal to a 1 plus cos theta. This is polar curve. So we use formula in polar. So the formula is formula for area is equal to double integration r d theta dr. Now where r is equal to a 1 plus cos theta. So I just try to locate this area here of the cardioid. It is something like this. So this is cardioid. R is equal to a 1 plus cos theta. This is theta is equal to 0. This is theta is equal to pi by 2. And here this is a. This is 2 times a. For theta is equal to 0. R is equal to 2 times a. Theta is equal to pi by 2. R is equal to a. and theta is equal to pi, r is equal to 0, and theta is equal to 3 pi by 2, again r is equal to a there. So we have to find out this area. So this area bound, I just find area of the upper half and make it 2 times. So this point is say A, this point B, and this point is O, that is pole r is equal to 0. So I make this A, B, O. So this and make it 2 times. So total area of the cardioid, total area means upper and lower half, total area, this is equal to 2 times the area of OABO, upper half, ABO, R d theta dr. I put the limits now. See how to get the limits there. Total area is equal to 2 times double integration ABO R d theta dr. Now to find out limits for this. See, limits we always draw a strip from the pole, radial strip from the pole in the region of integration. Here r is equal to 0, and at this particular point it is boundary of the cardioid. R is equal to a1 plus cos theta. So limits for r is equal to 0 to r is equal to a1 plus cos theta. And you have to move this, you have to move like this, you have to move this strip in order to cover this. Means theta is this position to this position. This theta is equal to 0 to theta is equal to pi. So these are the limits here. So we put the limits there. This is equal to 2 times r is equal to 0 to a. R is equal to 0 to a 1 plus cos theta, and theta is equal to 0 to pi r d theta dr. R d theta dr. So we simplify this with respect to r first all the time, because r having variable limits here. So theta is equal to 0 to pi, and here I put it in variable separable form. R is equal to 0 to a 1 plus cos theta into r dr, and then with respect to theta I integrate this. So this part I am integrating, integration of r, it is r square by 2. R square by 2 is the integration, and limits applied 0 to a1 plus cos theta d theta. This 2 gets cancelled. You may be getting 0 to pi. I apply the upper limit, a square 1 plus cos theta bracket square into d theta. I simplify this. This would be a square, this is a square 0 to pi. I open the bracket, this 1 plus cos theta bracket square, or I use the half angles, 2 times cos square theta by 2 bracket square into d theta, or this is equal to a square 0 to pi, this is 4 times cos raised to 4 theta by 2 into d theta. So it is 4a square 0 to pi cos raised to 4 theta by 2 into d theta. So I simplify this, put substitution, convert this to limit 0 to pi by 2 and use the reduction formula. Theta by 2 is equal to t. So d theta, this is equal to 2 times dt, and limits for theta is equal to 0, t is 0, and for theta is equal to pi, t is pi by 2. So these are limits you are getting. So this is 4 times a square with new limits t from 0 to pi by 2 cos raised to 4t d theta, it is 2 times dt. So 8a square multiplied by, I just take over here, this is equal to 4a square, 0 to pi by 2, 8a square, I'm sorry, 8a square cos raised to 40 dt. I use the reduction formula, 8a square, reduction formula, 4 minus 1 upon 4, 4 minus 3 upon 4 minus 2, 4 minus 3 upon 4 minus 2 into pi by 2. Now we simplify this, 8a square, this is 3 by 4, this is 1 by 2, this is pi by 2, this is pi by 2 is the last multiple there, this 8 gets cancelled, so your answer is 3 pi a square. So this is 3 pi a square divided by 2, this is area bounded by the cardioid. So this is the way you can find out area by using the double integration of the circle and this thing. Let's see one more example on area. Find area bounded by, find area bounded by, find area bounded by the curve y square 2a minus x is equal to x cube and its asymptote, So this curve, it is called Cissoid. So we have traced this curve already. So this curve would be Cartesian curve. So area formula, area, this is equal to double integration r dx dy, where r is this curve, r, it is this y square 2a minus x is equal to x cube. This is Cissoid. So this curve would be something like this. Details I'm not going to supply here. So it would be this curve. So you have to find area bounded by this. This is asymptote to this curve, x is equal to 2a, and this area you have to find out by using the double integration. I just find out area of the upper hat and make it 2 times. So this point is A, this B, and this C. So this is infinite, up to infinite. So we find out area of the upper half and make it 2 times. So let us see, this is area of the curve and its asymptote. So let us see. So this is 1. Now to find limits, what we do here? We find out limits for the upper half from here to here. We draw a strip, vertical strip. At this particular point, y is equal to 0 because this is x-axis and this is y-axis here. At this particular point, value of y. So this curve y square is equal to x cube upon 2a minus x. So y is equal to square root in the first quadrant, positive square root, x cube upon 2a minus x. So limits for y is equal to 0, lower end of the strip, and upper end, it is boundary of this, it is root of x cube upon 2a minus x. So root of x cube upon 2a minus x, and limits for x, you have to move the strip from x is equal to 0 to x is equal to 2 times a, x is equal to 0 to x is equal to 2 times a. So these are the limits for this. if you consider the vertical stream. So from 1, what you are getting, area bounded, area, total area, this or required area 2 times area of this AB, yes it is OABC, this area, it is dx dy. So upper half, and we have to find total area, so making 2 times there of OABC. So 2 times I apply the limits, y is equal to 0 to root of x cube upon 2a minus x, and x is equal to 0 to 2 times a dx dy. So I simplify this further. Simplify this. This is equal to x from 0 to 2 times a, and put it in variable with respect to y. We have to integrate naturally, because y having variable limits. It is this x cube upon 2a minus x into dy, and then with respect to x. So this is called variable separable form in y and x. So this is 2 times x from 0 to 2 times a. If I integrate this, so y 0 to root of, it is x cube divided by 2a minus x, so with respect to x. So this is 2 times x from 0 to upper limit and lower limit. It is you are getting root of x cube upon 2a minus x, and lower limit its value is 0, so with respect to x. Y upper limit minus lower limit. Now I simplify this further. I simplify. This is area is equal to 2 times 0 to 2 times a, 0 to 2 times a. I write down this as x raised to 3 by 2, root means x raised to, and 2a minus x, 2a minus x. This is bracket raised to minus half, and dx, like this. So this I can modify in this particular form. I convert this to beta function, put x is equal to 2 times a into t, because 1 minus t is the priority. So dx is equal to 2 times a into dt, 2 times a into dt, and limits for x is equal to 0, t is equal to 0, and for x is equal to 2a, upper limit, t is equal to 1, because 2a gets cancelled. So these are the limits you are getting. So this will convert area 0 to 1, x means 2 times a into t, bracket raised to 3 by 2, and then 2a minus 2a into t, bracket raised to minus half, bracket raised to minus half, bracket raised to minus half into dx is 2 times a into dt. I take all the constants outside here, 2 times a, bracket raised to 3 by 2 minus half plus 1. So this is bracket raised to 1, limits 0 to 1, 0 to 1, here t raised to 3 by 2, 1 minus t, bracket raised to minus half into dt. So this is 2 times, you are getting this as 2a 1 bracket square 0 to 1 t raised to, I can write 5 by 2 minus 1, 5 by 2 minus 1, and here 1 minus t, bracket raised to half minus 1, so it is minus half dt. So this is m and this is n. M is equal to 5 by 2. If you compare with the beta function, it is m and n, because beta mn, it is something like this, 0 to 1, t raised to m minus 1, 1 minus t, bracket raised to n minus 1 dt. So comparing with beta, so you may be getting this 2 times, this is 4a square, and this is beta. beta of 5 by 2 half. Let's simplify this. This is 8a square multiplied by, by relation between beta and gamma, gamma 5 by 2 gamma half divided by gamma 5 by 2 plus half. We simplify this further. 8a square into gamma 5 by 2 by reduction formula of beta function, gamma function. This is gamma half, this is gamma half divided by, this is 4 by 2, 6 means gamma 3. So you can simplify this further. 8a square, this is root pi, this is root pi. So pi you are getting. So 3 by 4 into pi divided by 3, gamma 3 means 2 factorial. So we simplify this. So this 8 gets cancelled. So 3 pi a square is the area bounded by this curve and its asymptote. So this is the way you can just find area in Cartesian or polar form by using the double integration. Well, hello students. See, to find length of the curve of some curve, length of the arc of some curve, or to find area of bounded by two curves, or to find some physical quantities like mass, center of gravity, moment of inertia, it is necessary to know the approximate shape of that particular curve. So there are certain curve which already you are knowing, but you don't know exactly what is shape of that curve. Like a straight line, you might have already learned straight line, different types of the straight lines, parallel to x-axis, parallel to y-axis, passing through origin, making some intercepts on coordinate axis. Similarly, circles also, different types of the circles you are knowing. So we try to know the Cartesian and polar equations of this thing. Like these three circles are there, like conic sections there, parabola, hyperbola and ellipse. So it is necessary for double and triple integrations, double integration, to know the approximate shape of this curve. And apart from these elementary curves, we are having some standard curves also, like cardioid is there, Laminscate is there, then folium of Descartes is there, asteroid is there, then Cissoid is there, standard curve. So this kind of the curve you must know. So we take one by one here, the straight line. Now if you observe the x-axis, y-axis, y is equal to mx is the straight line. Y is equal to mx is the straight line always passing through origin, and m is slope of the straight line. Similarly, equation of x-axis always y is equal to 0. Equation of y-axis is always x is equal to 0. And x is equal to a, if you take the line, it is always parallel to y-axis, and y is equal to b is the line always parallel to x-axis. So this is about the line. X upon a, y upon plus y upon b is equal to 1 is the line having the intercepts a and b on coordinate axis. So you can just check out this. Now x square plus y square is equal to a square. This is circle actually, having center at origin and radius is a, this circle, and polar equation of this circle is naturally x is equal to r cos theta, y is equal to r sin theta we are putting, and r is equal to a is always taken as the polar equation. R is the length of radius vector, so r is equal to a is the polar equation of this circle, and this is x square plus y square equal to a square is the Cartesian equation. Similarly, there are more circles here. If you observe this circle touching to x-axis, if you observe, so here center at 0 a, and here is the boundary 0 2 times a. If you observe, so this is x minus 0 bracket square plus y minus a bracket square, because center at 0 a and radius is a. If you simplify this, you are getting x square plus y square is equal to 2 times ay is also the form taken sometimes. Similarly, r is equal to 2 times a is the sin theta. It's actually the polar equation of this circle. So r is the length of radius vector, theta is the angle. So this is always taken as polar equation for the circle touching to x-axis, and touching to y-axis, it is r is equal to 2 times c cos theta there. The center at a0 if you observe, and radius is a of this circle which is touching to y-axis. Similarly, different parabolas here, y square is equal to 4x, this parabola. Mostly we need this parabola in double integration, so we should be able to draw this correctly with vertex at origin, and length of the latus rectum is 4 times a. Similarly, this parabola is symmetrical about x-axis because all the powers of y are even. Similarly, this parabola, if you observe, x square is equal to 4ay, even powers of x, so symmetrical about y-axis, and vertex at origin again for both the parabola because it passes through origin, and tangent at origin is y is equal to 0 by equating lowest degree term. So this is parabola. So you must know the approximate shapes of this curve. Now this is ellipse actually, x square upon a square plus y square upon b square is equal to 1 with length of major and minor axis a and b respectively. This point is a0, this point is 0b, and a is greater than always b there. Now next curve, it is this r is equal to a 1 plus cos theta. This is cardioid, standard cardioid actually. So this cardioid, if you observe, theta is equal to 0, r is 2 times a. Theta is equal to pi by 2 if you are putting r is equal to a. Theta is equal to pi, r becomes 0. And theta is equal to 3 pi by 2. If you go further, then r again a here, and again theta is equal to 2 pi, it is 2 times a. So this is standard cardioid. If you take minus sign here, it is inverted like this. So it is this cardioid. And if it is taken as plus sign, then you are having those cardioids already I have given there. So this is standard curve cardioid. Similarly, if you take this, observe this curve, r square is equal to a square cos 2 times theta. This is called Laminscate of Bernoulli. So this curve also important actually to find this arc length or for finding area of one loop of the curve. Similarly here also for arc length of cardioid, area of one loop, full cardioid or the portion of the cardioid located above the initial line, and so on. So this is also important curve. It is r square is equal to a square cos 2 times theta, dumbbell shaped. So there are two loops in this particular curve. Similarly, you are having some more curves here like x cube plus y cube, x cube plus y cube. Next curve is x cube plus y cube is equal to 3 times axy. So this curve is known as folium of Descartes. Folium of Descartes. So you must know shape of this particular curve. It is something like this. This curve, if you try to trace, it is standard curve. This is loop formation at this particular point, origin, and it is symmetrical about initial line y is equal to x. It is symmetrical about initial line. It is symmetrical about the line y is equal to x, and this curve. So it is something like this. It is going like this, and here is the asymptote for this particular curve. So you must know shape of this approximate shape of this curve. It is folium of Descartes. This is x-axis. This is y-axis, and so on. So this equation, this curve. Then next is x raised to 2 by 3 plus y raised to 2 by 3. This is equal to a raised to 2 by 3. So this curve is actually this is called asteroid, star shaped. Asteroid, this curve, it is called, it is star shaped. This it is something like this. It is seems to be a star. I draw it again. So it is something like this curve. So it is this. This is A. This is A. This is minus A. This is minus A. So you must know this equation and parametric equation of this also. X is equal to A cos cube t, y is equal to A sin cube t. These are parametric equation of the asteroid. This is x-axis, this is y-axis. So these are the cusp at these particular points there. And this curve, it is, sometimes you need to find length of this. So length means this point A0, this point 0A. You take parametric equation, it is always convenient to take. So t is 0, pi by 2, or area you need to find out of this. So you must know approximate. You need to find area of the loop of this particular curve or length of the loop. So for this we need this standard curve over there. Similarly, we are having hypocycloid also. Hypocycloid is the curve x by a bracket raised to 2 by 3. Same type y by b bracket raised to 2 by 3. This is equal to 1. So this is hypocycloid. It is something like same curve actually. It is something like this. This is A, this is B, this is x-axis, this is y-axis there. Similarly, spirals are there, then limacon. So this type of the curve you must know there. And if you know the approximate shape of this curve, you can find arc length, you can find area bounded, or you can find some other physical quantity, mass, center of gravity, moment of inertia, and so on. That's all.